Right. So today, as discussed, we will look at the tutorial on the DC machine dynamics. So in tutorial question 1, we're looking at a separately DC excited generator. And the parameters of the machine are given, right? So the value of RF, your field inductance, armature resistance, armature inductance, and the constant Kg. And we are also, it's also given the speed of the generator, the DC generator. And initially the field and armature are open. And at time t is equal to t0, basically we've switched on the supply, right? So we applied a 250 volt source to the terminals of the field winding, and we asked to find the equation for the terminal voltage as a function of time, right? So if you remember, we had this equation for the field winding. So one part is representing the drop across the resistance of the field winding, and the term IF SLF is basically representing di by dt, if you remember from the time domain response. So this is the Laplace transform of that equation. So as you can see here, I've basically made IF subject of formula to represent the voltage, and that's your term in the denominator there, RF plus SLFF. And the armature voltage is given by Kg times IF, right? So these two equations we can basically substitute there. And as you can see, when you substitute IF in this equation here, you end up with VFS Kg over LF. I've factorized LF outside, and that gives us 1 over tau F plus S, where tau F is LFF over RF, right? So this is your equation for the armature voltage. So as we said, at time t is equal to 0, we applying a step input to the field winding. So VFS is equal to 250 times 1 over S, and that's the voltage that's going to be applied to the field winding. And we can also work out the time constant of the field winding, the ratio of LFF over RF. We can work that out. So when you substitute, so this term 1 over TF will become 2 here, right? And Kg over LLF is here, and VFS is 250 over S. So you end up with this transfer function for the armature voltage. And using your Laplace transform table, you can convert this back into the time domain, and you end up with this exponential rise in the voltage. So that's 250 into 1 minus exponential of minus 2 times t there. So it's exponentially rising to 250 volt, the output of your armature voltage. Okay, so that was for the first part that's given in the question. And basically in part B, they ask you to work out the steady state condition, right? After the steady state condition have been established, the armature is now connected to a load resistance and an inductance of this value in series, and you're asked to work out the armature current and the terminal voltage as a function of time. So let's go back to the circuit. So we're adding a load resistance and an inductor in series with the motor. And so basically now when you switch, when at t is equal to 0, you close the switch, basically the armature current, the current that's going to flow in the circuit, will be the armature voltage, which is from here, and divide by the total resistance and the total inductance there of the circuit. So the total resistance is RA plus RL, and the total inductance is LAQ plus LL. So remember that term is, remember it's di by dt, so that's why it's got the S term there. It's got a differential because of the di by dt when you're transforming into Laplace transform. So same as we did here. This term here, remember, it was I times S, basically LFF. So your inductance term will involve that S term here. Same we will basically repeat the same here, right? So it will be S times LA dash. Right, so when we're looking at steady state value of the armature voltage, remember the this value EAS, sorry, is 250 over 1 over S. Remember that's a step voltage of 250 volt that was applied to the field winding, and we can work out the total value of RA dash and LA dash, so that's just substituting there. And to get the current now, we will basically take the voltage times 1 over this this term here, which is, we've factorized LA dash outside, so you end up with S plus 1 over tau A, where tau A is RA dash over LA dash. And basically, when you substitute, you end up with this term here, which can be simplified as 200 times 625 over S into S plus 625, right? So this term, basically you can, when you do the inverse Laplace transform, you end up with IAT, which is equal to 200 into 1 minus exponential of minus 325t. So that will be your current in the steady state current in your armature, right? So in terms of armature terminal voltage, so basically now, if you want to get that voltage, you're going to take your current, right? So you're going to take your armature current multiplied by only the load section, which is RL plus S into LL. And when you do that, as you can see, we're going to use the equation we got for the armature current here. So that's the term IAS, and we'll multiply it by the load section, which is RL plus S LL. Okay, so that's in your S domain. You end up with this function here. So the terminal voltage for the machine is given by this expression, which now, when we want to basically work it out in time domain, first we need to do a partial fraction expansion in this in those two terms here, right? So if you remember your partial fraction, if you have an S into S plus 625, this kind of format, so it will have two terms. If you expand it using partial expansion, you'll have A over S plus B over S plus 625, and then you can basically expand, right, and solve for A and B. So how you get B is you basically cancel this term by inserting minus S is equal to minus 625, and you solve for B. Then to get this term here, we can use basically any term here. I've used S is equal to 1. That basically give you both term A and B, and when you solve, you can work out what is the integer A there. So we got A and B, and then we can write the terminal voltage into two terms, where you can easily now basically do the inverse Laplace transform. So the inverse Laplace transform from this term gives you 240, and the inverse Laplace transform for this section gives you minus 252.5 into exponential of minus 625t. So that's how basically your voltage will look like for in the time domain with this particular load across the machine. Right. So this was for section B, where we were asked to work out the armature current and the terminal voltage as a function of time. In the last part, they asked us to work out the electromagnetic torque as a function of time, right? So the electromagnetic torque will be basically your power, the electrical torque divided by the speed of the motor. So here in the S domain, we have those two functions, which is EAS and IAS. So basically, also remember that in this motor, the speed is constant, right? So given to us that the generator is driven at constant speed of 1,200 RPM and constant. So if your speed is constant, then the armature reaction can be neglected, and so your EA is also constant. So when we solve for the for this term here, which is your electrical torque in the S domain, so we will use the voltage as 250, and omega, you need to work it out. So that's 2 pi 1200 over 60, right? So that will give you the angular frequency of the machine, omega, sorry, the speed, which is omega, and the IS term is basically substituted here. So again, you end up with an equation that you can basically do the inverse Laplace transform directly. So you end up with this term here, which is 398 into 1 minus exponential of minus 625t Newton meters for the electrical torque in the generator. Okay, so as you can see, the all the terminal voltage and the torque is also basically following the same structure. It will have an exponential rise in the and attain a steady state value for the torque also. Right, so this is for basically question 1, which is based on this separately excited DC generator. Question 2, we also got the same structure where we've been given the parameters, right? And in part A, the generator is also driven at rated speed, and the field circuit voltage is 200 volt is applied to the field winding. So we'll look at question 2. Right, so you can see there I have basically worked out this time constant that is basically having the same formula, which is LFF over RF. So I've worked out this time constant, and so also using equation 17 from your notes, that will be the voltage EAS for the DC generator. and your field circuit, you will have basically the same principle that we've used in the previous question. So you'll have Vf times 1 over S for the field voltage, and the armature voltage then will be the product of this Vfs into this whole equation here, right? So substituting, you will end up with this expression, which can basically be inverse Laplace can be applied to it, and you end up with this expression for the voltage for the armature in the time domain, where you have basically kg times Vf over Rf into 1 minus exponential of 1 over tau times t there. So I've basically substituted the values and worked out the expression for the armature voltage, right? So that will give you the expression, and in part B, they ask you the steady state armature voltage, and in part part 3, they ask you the time required for the armature voltage to rise to 90% of its steady state value. So I've done this solution. So when you insert here for steady state value, so this term will basically cancel as t tends to infinity. So this basically turns to 0. So you end up with EA being equal to 200 volt. That's your steady state value. And for the second part, so for us to reach 90% of 200 volt, so you insert that here and solve for basically for the variable t. So you take the expression and you multiply by 0.9 times 200 and solve for t, and that basically gives you the answer here. So that's 0.5756 seconds for the machine to basically rise to 90% of its steady state voltage. Okay. So for part B, it's the same process that we've done. A load is being added to the generator. So we've added LL and RL to the inductance and the resistance of the armature, and that will give us tau A. You can work out that the time constant, and here again, this is your equation for the armature. So it's IAS times those two terms, RAT and LATS times IA. So making IA the subject of formula and substituting. So this is your expression for the current, right? And here I've basically expanded the expression. So you will end up with, remember this section comes from here, from this formula here, right? So we have EAS, and we got these expressions here, and again here I've basically substituted EAS with that expression, and then you have this term RAT 1 into S tau 80. So that section is here. So you end up with this long expression here, which got basically all the constants of the machine times the two time constant, which have been factorized out of those denominators there. So you will end up with 1 over tau and 1 over tau t as tau f and tau at there. So those two terms have been factorized out. And then I've substituted all the time constants and the values here. So that's the expression that you come out with, right? And when you simplify, you end up with this expression, okay? So again, as you can see, for you to now solve for the time domain response of the working with the current, armature current. So you'll have to apply partial fraction expansion again. So now when you expand those, you see you have three terms in the denominator there. So when you expand this into three partial expression, fraction expansion, so you have a over s for the first term, b over s minus 4, that's your second term in the denominator, and c for the third term in the denominator, right? And so when you basically expand, you end up with this expression. And now for you to determine a, b, and c, you have to substitute values for s, right? So as you can see, for you to get the term a, we have to cancel those two terms, and that's being done by inserting s is equal to 0. You'll end up with only the first term, and that then you can solve for the value of a. To get the value of b, so this term, we have to substitute s to be minus 4, so that will cancel, this to return to 0, and here return to 0. So we cancel the two term a and c, and we solve for b there, okay? And last one, to get the c term. So here we substituted to cancel the first two terms. So it's minus 7.353. So that will cancel, those two terms will turn to 0, and you can solve for the c term, as you can see there. So when you write now the current in terms of partial fraction expansion, there are your three terms with a, b, and c in the numerator. And then you can apply your inverse Laplace transform to get the expression for your armature current. Okay, so this is how we apply the material that you have learned in mathematics now into machines to basically use your inverse Laplace transform to solve for example, the armature current in a DC generator. Okay. The next question is on a motor, a separately excited DC motor, and here we've been given the information. For example, here we know that the motor generates a certain armature voltage at rated speed with a certain field current, and we also know what is the load torque, right? And what is the combined inertia of the motor and load, and what is the armature DC voltage supply. So that's 220 volt, and the field current is also 1 amps, right? So we are asked to derive expressions for the speed and armature current as functions of time, and then to determine its steady state value of the speed and armature current. Right, so that's all question 3. So we'll start with the basic equation for a DC motor, where your induced voltage is proportional to your speed of the motor. Right, so we know what is the applied voltage to the armature. Right, so the armature is connected to a 220 volt DC supply, so that's 220, and we know that the speed is 2000 RPM, so we can basically work out what is Km. So we substitute and solve for Km, so that's 1.05 V, so that's a volt, it's radian, second per radian here, because you got your speed in the denominator, and when you raise the unit up, it inverses it, so now it's second per radian, right? So the terminal voltage for the motor will basically be the sum of the armature induced voltage plus the drop across the armature. So we end up with Km omega m plus Ia Ra, and the torque, the total torque on the motor is the sum of the load torque and the inertia of the motor times d omega by dt, right? So we can also work out what is this value of torque. So that's given by Km times Ia, and hence to get the voltage, the terminal voltage of the motor, I've substituted the equations there. So this term here is basically J over Km times, so basically the these equations come from your notes. You'll need to refer to your notes to basically get the voltage of the terminal voltage of the DC motor. And then I've substituted the equation for the, you will see there, Km omega m is here, this term, and Ra is here, and I've substituted Ia, which basically now I've sent Km onto this side. So that's the term that you have here in between the brackets there. Right, so when you expand here, you end up with this, so three terms for the terminal voltage. And simplifying, you have basically these three terms that I've written in time domain format. And here, basically, I've applied the Laplace transform for this particular situation where you basically have a field voltage that's applied at 220 volt there. So with this step in the field voltage, the terminal voltage of the machine then will be 220 over S. That's your step voltage. And that's the expression that we apply Laplace transform. So you end up with 1.05 omega ms. This one will become, this is a differential of omega m, so it will be S omega ms. And this one will become, the constant will become 11.9 over S. Right, so that's applying Laplace transform to this equation. And then we can basically solve for omega m. So again, you can see that to simplify the equation in Laplace transform, you will need to apply partial fraction expansion and basically solve for a and b. And from there, do the inverse Laplace transform to get the equation for your speed of the motor. So as you can see, you're getting an exponential rise in your speed. And the steady state value, we will work that out in the next part. So for the current in the motor, so that's given by Vt minus Ea over Ra. So I've substituted the value of Ea as Km omega m from the previous expression that we had there. So going back here, right, remember Ea is given by Km omega m. So when you substitute, you end up with this expression here for the current, right? And we know what is the solution for omega m, so we can substitute here and basically get the expression for the armature current. Okay, so that's how you basically get the expression for the armature current in the time domain format. So for steady state speed and current, so remember that this term will basically become 0, right? So you end up with 1 98.2 radian per second for the steady state speed. And for the current, again, this term will turn to 0 when you have steady state, and you end up with IA being equal to 23.8 amps. Right, so that's the steady state solution for your current, armature current, and the speed of the motor. Right. The question 4 in the tutorial is on the last part that we did, which is the speed control of a DC motor. So the parameters of this system is basically given. What is RA, LAQ, your moment of inertia, motor plus load inertia, that's J is equal to 0.2 kg meter squared. The voltage constant Km is given, speed voltage constant Km, and the tachometer constant is also given. Right, so this speed control system is working on a 10 horsepower, and that's 1750 RPM and 240 watt, a separately excited motor. Right, so in this question, the reference voltage is adjusted such that your motor is running at 1800 RPM at no load, and the gain is adjusted so that the damping ratio delta is 0.5. The corresponding values for damping factor alpha and undamped natural frequency omega n and Ka must be worked out first. Okay, so let's look at what's given to us. So this constant is your tachometer constant, 0.1 watt per RPM. So we basically now converting it from RPM to radian per second. So KT is 0.1 volt over RPM. So now when you basically now convert that to radian per second, so it will be divided by 2 pi over 60, and when you send the unit up, it will become second per radian there. And the two time constants, tau A and tau M, can be worked out from the parameters given. And the damping factor of the motor is given by 1 over 2 times tau A, so that can be worked out. The natural frequency omega n is given by alpha over delta, so that can be worked out. And again, from your notes, this equation is given. So omega n is given by square root of 1 plus k naught over tau A tau m. So we can solve for this constant k naught. That becomes 21.22. And hence we can work out what is the gain. Okay, so remember the question, they asked us to work out the amplifier gain Ka. So that can be worked out. Once you've worked out K naught, it comes out to be 28.22. Right, so that's your amplifier gain. Right, so next part of the question, they ask us to basically, with the system initially at steady state and no load condition, a step load of 40 Newton per meters is suddenly applied to the motor shaft, and we're asked to work out the final steady state values of the motor speed and the motor armature current. Okay, so again, we're using the equation that we've derived in the notes. So that's basically delta omega m at steady state. So we need to basically use this equation here. The step load torque is 40 Newton per meters, so that's substituted by 40 here. And RA, Km, and K naught is substituted. and that basically gives us the steady state speed of the motor. Okay, so that's the steady state change, which is delta omega m. So to get the steady state speed, we need to take omega naught minus the steady state delta omega, right? So the motor, remember, is basically working at 800 RPM at no load, and so by subtracting this delta omega m, we get basically the steady state speed of the motor, right? And to get your armature current, so that is TL over Km, you can work it out there. So that's 31.5. Right. So for part B, they ask you to find the initial values of the speed and armature current. Right. So now you're basically remember that at no load, the motor is basically running at 1800 RPM, and obviously, if there is no load, the armature current is initially at zero value here. So IA is zero, and your no load speed is 1800 RPM. Now the next part, they ask you to basically work out the initial rate of change of speed, right? So for us to get that, we need to apply this final value, the initial value theorem, where we're looking at t is equal to 0, right? So when t tends to 0 for ft, the limit for in the s domain is s times fs, where s is tending to infinity. So we apply this this theorem to this expression that we have for the speed control system of a motor, and basically solve for this final value. Sorry, this speed, the value for the speed of the motor. So this expression for s omega s there is given by this expression from your notes, right? And now when you apply this initial value theorem here, you basically end up with a simplified equation here, which is minus r times a over km squared tau m times delta t. So it's just a matter of substituting the values that that is been given in this question. So the rate of the change in the load is 40 Newton meters, and R, A, Km, and tau m is given. So you can work them out and substitute. So you end up with minus 200 radian per second for this initial rate of change of speed for the motor. Okay, so basically, as you can see, this last tutorial in the last chapter is mostly application of Laplace transform and then inverse Laplace transform to basically go back into time domain. And you need to basically make sure you understand how partial fraction is applied in the S domain to expand, and then makes your inverse Laplace transform easily. And also you must be able to basically apply the equations, for example, for the armature voltage and also the armature current in Laplace form, so that then you can basically solve it for the time domain eventually to get the final values. So just take note that normally this is provided in the test question. So I will provide you those basic equation for the closed loop control of a DC motor, and I will also give you the table for the Laplace transform. to basically enable you to initially apply the Laplace transform and basically solve for the question for the variable that you need, and then also apply inverse Laplace transform to basically go back into the time domain to basically, for example, sketch your voltage or your current or your torque for the machine. Right. So if you have any question, please you are free to discuss now. Please let me know. All right. So there's no questions. So I will post this tutorial solution onto the learning page, and so basically we won't have lectures on Friday. So basically we'll meet next week Monday on the 17th for your test 2. I will try and release the marks for test 1 by Friday. So um, just check on. I will release it on Student Central by Friday latest, and also I'll post the solution for test 1 when once the marks are released by Friday. Okay, so revise for your test 2 for next week, Monday at 12:30 to 1:30 via the learning website. Cheers, guys. I will end the session now.